Assalamu alaikum. In this video, I will discuss about the relationship between three types of vector space. They are metric space, normed space, and inner product space. To understand the relationship between them, first we have to know what is vector space, what is metric, norm, and inner product. First, let me show you the relationship between them. Metric space. Metric space is superset of normed space. Normed space is superset of inner product space. So what does this mean? If we take a element from normed space, then this should necessarily be a metric space. But not all metric space is normed space. Similarly, not all normed space is inner product space, but every inner product space is normed space. So this is the relationship between them. Now let us know about vector space. What is vector space? Vector space is something that defined on a non-empty set and a scalar field K. A scalar field uh, K contain scalars and vector non-empty set contains some vectors. If the vectors of this set follows the 10 axiom, follows this 10 axiom, then this vector is called vector space. So what are the axioms? The axioms are close under addition, commutative law, associative, additive identity exists, then additive inverse exists, closure under multiplication, distributive law exists, distributive law for vector addition and distributive law for scalar addition exist. Associative and associative for multiplication, scalar multiplication and multiplication identity exist. If the elements of the set V follows these 10 axioms, then the set V is called a vector space. Now more specifically we will define metric space. What is metric space? Metric space is also defined on a non-empty set X. And the metric, what is a metric? Metric is a mapping, more specifically a distance function, which follows these four properties. The properties are d of x y, that is the two element x and y from the set X. Then if we apply metric on these two sets, two elements, then this is always non-negative. And the metric of dxy is equal to 0 if and only if x equal to y. Then this is symmetric, then triangular inequality follows. So what is metric? Metric is a mapping which follows these four properties, and a space x and a space x with this metric D is called a metric space. Now we will define norm. What is norm? Norm is also a kind of mapping which follows these four properties, which are this: non-negativity, norm of x equal to 0 if and only if the element x is equal to 0. Norm of scalar multiplication is defined as norm of alpha x equal to modulus of alpha into norm of x, and here also triangular inequality follows. We see that norm can be defined also as metric. If we define a matrix such that norm of x minus y, then this is the usual norm defined or expressing using metric. So now we know about metric and vector space and norm. Now we'll back to our relation. So now we'll see why this inequality or why this relationship follows using counter examples. So our first example is the space R with a metric defined as this. We can prove that this is a metric space, but this is not normable, or this is not a normed space. That is, we will taking an element from metric space but which is not a normed space. Why this is not normed space? We can see that we know the scalar multiplication of norm, that is metric of two element equal to modulus of that scalar into metric of individual elements. If if we put a element as 0 and a element lambda x in this matrix, then this is not follow this property, this not follow this property. So this is a metric space, but this is not a normed space. Our first relationship holds. Now we will see a normed space, LP space, which is a normed space, but it is not a inner product space. To prove this, we will prove this using the parallelogram property for inner product space. What is this? This is if we consider a LP space. So what is LP space? LP space is if we consider a sequence x equal to a sequence such that the element of sequence, if we take the summation of xi I to the power p, which is always finite, or which is always finite less than infinity. So this kind of sequence are elements of LP space, or LP space is formed using these types of sequence. So we are saying here that LP space is a normed space, but LP space is not inner product space. So we define a norm on LP space such that norm of x equal to summation I equal to 1 থেকে infinity xi I to the power p whole to the power 1 by p. This is a norm on LP space. Now we are taking two elements from LP space, that is 1 1 0 0 1 minus 1 0 0. These are the elements of LP space because these two element follows this property. These two element follows this property. Now we will find the norm of x, norm of y, norm of x, norm of y using this norm definition. Then norm of x plus y. Now parallelogram law, what is parallelogram law? Parallelogram law is norm of x plus y whole square plus norm of x minus y whole square is equal to 2 into norm of x square norm of y square. But from this calculation we can say this equality doesn't hold. So LP space is not a inner product space because this doesn't follow parallelogram law. We already know that for to hold inner product space, a space should follow this parallelogram law. So our second example is done. Now we will discuss about complete space. What is complete space? Complete space is if we take a sequence from a space, then the sequence converges to that space. That is, if we take a sequence from metric space and the sequence also converges to that space, to a element of metric space, then the space is called complete. So complete metric space is complete space, complete normed space is called Banach space, and complete inner product space is called Hilbert space. So this general space plus completeness, if we see the relationship between general space plus completeness, that is complete space relationship is defined as complete metric space is superset of Banach space, Banach space is superset of Hilbert space. So to see the relationship, how the relationship holds, we can consider the above two example here as well. How? That is, one is a complete metric space, one, that is this space is a complete metric space, we can prove this, but this is not Banach space. Why this is not Banach space? We already showed that this is not normed space. So this is already not normed space, then this can't be a complete normed space. So this is not a Banach space. And also 2, LP space, we said that LP space for p not equal to 2 is a normed space. For p not equal to 2, LP space is a normed space but not inner product space. So for p not equal to 2, LP space is not inner product space, so it can't be a complete inner product space. Also it can't be a Hilbert space. So Banach space but not Hilbert space. So we can see the relationship, if we summarize the relationship between these spaces, it is that metric space is the superset of normed space, inner product space, then inner product complete metric space subset of Banach space subset of complete complete space, Hilbert space subset of Banach space. Then Hilbert space is subset of inner product space. How? Not all inner product space are complete, but only the complete inner product space are Hilbert space. So Hilbert space is a subset of inner product space. Similarly, Banach space is a subset of normed space, because not all normed space is complete. Only the complete normed space are Banach space. And complete metric space are subset of metric space, because not all metric space is complete. So only the complete metric spaces are called complete. So this is a subset of metric space. This is the relationship between three type of spaces or three type of vector spaces.